Hey guys, today we're going to be learning about net ionic reactions. So this is going to be building a lot off of something that we did in Unit 3 when we were talking about solubility. And we were talking about how things that are insoluble stay as like a whole when they're in solution, and things that are soluble break apart into the ions in like a form of like a dissociation reaction. So we're going to be building a lot on that kind of stuff that we did back then. So some of this is definitely going to seem like review. Okay, so with these net ionic reactions, we're going to be dealing mostly with single and double displacement reactions since they involve mostly ionic compounds. We're going to be writing and balancing full ionic equations, which you would have had lots of practice with at this point. Also identifying precipitates using your solubility table, which we did in Unit 3. And then the two kind of new things that we're going to be doing is identifying spectator ions and then writing and balancing net ionic equations. So the full chemical equation or the molecular formula is just like the normal reaction that you write, where you have the reactants and the products. Nothing is dissociated, everything is still in its like full compound form. Yeah. Even though this is all taking place in water or in an aqueous environment, we don't actually write in water because it's not a reactant. If you would like to, in little brackets, put AQ for aqueous, you can do that. But I just don't bother, to be honest. So yeah, in the full ionic equation, like I said, don't actually dissociate the ionic substances at this point, even though in reality, most ionic substances will dissociate in solution. And that is, of course, because the polar ends of the water pull apart the positive and negative ions that make up the ionic compound. So what we're going to be doing is taking these full ionic equations, identifying the precipitate, and then dissociating everything else. When we were in Unit 3, we dissociated the non-precipitate product, but in this case, when we write the full ionic equation, we're also going to be dissociating the reactants. So that's what makes this different from what we did in Unit 3. So when you write a full ionic equation, start with the full chemical equation, which again is the one where you have the compounds and no ions anywhere. Then you're going to identify any products that are slightly insoluble on your solubility table, and that will be your precipitate, and it will stay as a compound. And then all other products and reactants are going to be dissociated into ions. And then you just balance it. Okay, and then again, if you want, you can write like the AQ behind everything. There would be a little S behind the precipitate to show that it's a solid. But again, you don't have to worry with that final step for me in Chem 20. Just a reminder, ions are not diatomic. So please do not write any of your ions with a little 2 behind them. Okay, so we're going to work through this example together. I do have it all written out there. So the way that this would work is you would start off with your magnesium sulfide and your sodium hydroxide. Again, don't forget to cross over your charges. In this case, the charges of magnesium and sulfur cancel out because they're both 2. And then Na and OH both have charges of 1. Then we are going to do a double displacement. So our 2 metals will swap positions. So we will end up with magnesium hydroxide and sodium sulfide. Again, don't forget to recross your charges. The charge of magnesium is 2, which is why we have OH2 here. And the charge of sulfur is 2, which is why we have Na2. And then we're going to balance this, and in order to balance this equation, all we have to do is put a 2 in front of the NaOH. Then we're going to use our solubility table, and we're going to check both of our products to see if either of them are precipitates. And when you do that, you will see that magnesium hydroxide is only slightly soluble, so it is going to be a precipitate. Sodium sulfide is very soluble, so it will not be a precipitate. Then we are going to rewrite everything as ions. So we're going to dissociate every single compound in the equation except for the precipitate. So our magnesium sulfide gets broken apart, our sodium hydroxide gets broken apart, and our sodium sulfide gets broken apart. Again, it is only the magnesium hydroxide, the precipitate, that stays whole. And then we balance our equation once again. So in order to have this fully balanced, we will have to put a 2 in front of the Na, in front of the OH, and in front of the other Na. It is important to notice that when you're balancing these, they don't only have to be balanced with like the products and reactants, they also have to be balanced with the original full chemical equation. So that's why I had to put 2's in front of the sodium ions, in front of the Na pluses, was because in my original equation, I had 2 NaOH. And then your last step, again, is to just put in the like aqueous and solid symbols. Again, I don't care if you do that last step or not. If you just kept your final answer, what you see here in step 5, I would be totally happy with that. Once again, make sure that when you do this, your precipitate should be the only thing that doesn't have a charge. Everything else is an ion, so everything else needs a charge. Okay, so practice writing these ones and then come back and check for the answer. Okay, so these should be your answers. So for the first one here, I started off by writing out my full chemical equation. So this is lithium carbonate. Again, carbonate has a charge of 2, which is why it's Li2CO3. And then calcium nitrate. Calcium has a charge of 2 that crosses over outside of our nitrate. Nitrate has a charge of 1, so we don't bother writing it. And then when we do our double displacement, we end up with lithium nitrate and calcium carbonate. Then I use my solubility table to identify the precipitate. So if we look at nitrate here, it says that all things are very soluble. So lithium nitrate is definitely very soluble. Our carbonate ions over here, it's only very soluble with group 1 elements as well as ammonium. And calcium is a group 2, which means that it falls into the most category that is a precipitate. So then I break both of my reactants apart into the individual ions. I break my very soluble compound into the individual ions, and I keep my precipitate whole. And then I just make sure that it's balanced, both with obviously both sides, but also with the original equation. So because I had 2 lithium here, I put a 2 in front of my lithium ion on both sides. Because I had this 2 here, not only does my lithium need to get a 2, but so does my nitrate. My nitrate also needs a 2 on the other side because of this little 2. Okay, and so that should be your answer. 2 Li plus CO3 minus 2 plus Ca plus 2 plus 2 NO3 minus becomes 2 Li plus 2 NO3 minus plus CaCO3. And sorry, this is kind of jammed in there. That is a little 2 that I've squished in there. For the second one, we have aluminum bromide and potassium sulfide. Again, don't forget to cross your charges. Then we do our double displacement. Again, recrossing our charges. Then we're going to check our solubility table, and you'll see that aluminum sulfide is a precipitate, while potassium bromide is very soluble. We will balance everything with a 2, a 3, and a 6. And then split apart both reactants into the ions, split apart your very soluble product into ions, and keep your precipitate whole. So you should end up with 2 Al plus 3 plus 6 Br minus plus 6 K plus 3 S minus 2 becomes Al2S3 plus 6K plus 6Br minus. Okay, so then we move on to our spectator ions. And spectator ions are the ions in an ionic reaction that don't form the precipitate. So when you see the full ionic equation written out, you'll see that sometimes on either side or on both sides, you'll have the exact same ion written. Essentially, those can just get canceled out. They don't actually do anything. So we call those our spectator ions. Essentially, after the dissociation takes place, they don't really create a new product that wasn't already there. They just stay in ion form. So yeah, our spectator ions get canceled out. So this is an example of what that would look like. This example here is a full ionic equation. It's actually the same full ionic equation that we did as our first example. And you can see here that I have 2 Na plus on both the reactant and product side. I also have an S minus 2 on both the reactant and product side. Those two ions are our spectator ions. And then when we create a net ionic equation, it's essentially just canceling out those spectator ions. We don't include them in the final net ionic equation because they don't make a new product once you've dissociated them in solution. It is important to note that when you're canceling out ions, make sure that both of them are actually ions. So an Mg plus 2 will cancel out another Mg plus 2, but an Mg will not cancel out an Mg plus 2. So they have to both be ions in order to cancel out. If one of them's a solid, even if it's by itself, it won't cancel out. And I'll show you in a moment what that will look like. But if we took the example that we did for our first full ionic equation, like I said, we would cancel out the 2 Na plus because that ion is on both sides, and we would cancel out our S minus 2 because that ion's on both sides. And in the end, our net ionic equation would just be our magnesium ion plus our 2 hydroxide ions would make magnesium hydroxide. And so that little note at the bottom is what I was just talking about there. Solid reactants do not get written as ions, just like precipitates don't get written as ions. So yeah, just keep that in mind. So let's do a second example that takes that into account. So here I have silver nitrate, which is AgNO3 reacting with aluminum. If I do my double displacement, I'll get aluminum, nitrate, and silver being formed. Now, when I turn this into ions, my ionic compound of AgNO3 gets broken apart into its ions, but the aluminum is not an ionic compound because you need a metal and a non-metal to be ionic. So aluminum is just a hunk of metal. So I don't write aluminum as an ion when I do my full ionic equation. As you can see here, it doesn't have a charge. It is a hunk of aluminum. It is not an ion. And then when I did my double displacement, I made a ionic compound, my aluminum nitrate, and I would check to see if it's a precipitate. And if it's not a precipitate, I break it apart into its two ions. But I also made a hunk of silver, and that hunk of silver is not an ionic compound because an ionic compound is a metal and a non-metal, and this is just a metal. So this hunk of silver, this Ag that I have here, is not an ion. So when I write my full ionic equation, it still isn't an ion. So when I'm then looking for my spectator ions, I have a silver ion on one side and a hunk of silver on the other side. Even though they're both silver, they don't cancel out because only one of them is an ion. I also have 6 nitrate ions on both sides. Those will cancel out. And then I have a hunk of aluminum and an aluminum ion. Again, one is a solid, one is an ion. They don't cancel out. So my net ionic equation is my silver ion plus my solid aluminum becomes an aluminum ion and solid silver. Okay, so note that the silver and aluminum ions did not cancel out because on either side, one of them wasn't an ion. The only spectator ion in this example is the nitrate ions. There were ions on both sides. So I'm going to let you guys try these 3 examples, writing the full chemical equation, the full ionic equation, and then the net ionic equation for each of these, and then come back and check your. Okay, so these are the 3 examples. So we started off with barium sulfate reacting with beryllium iodide, and we do our double displacement reaction. Then we break both reactants down into ions. Your beryllium sulfate is going to be your precipitate. Your other product gets broken apart into ions. And then you cancel out your spectator ions, which are the ones that are the exact same on both sides of the arrow. Whatever does not get canceled out becomes your net ionic equation. For the second example, we had gold reacting with aluminum sulfate to become gold sulfate and aluminum. Then we break apart our ionic compound. Again, gold, being that it's only a metal and not a metal with a nonmetal, is not an ion, so it stays as just gold. Our ionic compound gets broken apart, and then if you check gold sulfate on your solubility table, you'll see that it will be a precipitate, so it's not going to break apart. And then our aluminum was solid aluminum, not an ion, so it's not ionic either. And so this reaction actually won't have a net ionic equation because there are no spectator ions. So all you have is the full chemical equation and then the full ionic equation. And then for the last example, we have iron bromide reacting with nickel to make nickel bromide and iron. I didn't tell you what the charge of nickel is, so you can give it whatever charge you want. To be honest, a charge of 1 is the easiest. Then we break apart our iron bromide since it is a ionic reactant. It gets broken apart into the ions. Nickel is not an ionic compound, so it stays as just nickel and does not become an ion. And then nickel bromide, if you look on your solubility table, is very soluble, so it gets broken apart into its ions. And then iron, our Fe, again, is just a metal, not an ionic compound, so it will stay as a metal and not an ion. Then we cancel out our ions that are the same on both sides, which are our 2 bromine ions. Nickel is not going to get canceled out because it's an ion on one side and not the other. Same with iron, is an ion on one side and not the other, so it doesn't get canceled out. So our final net ionic equation looks like this.